Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure. The phase diagram of water shows if water is in its gaseous, liquid, or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. The vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperatures below 100 degrees Celsius if a static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure. The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. But how is it possible that the pressure becomes very low in certain areas of a fluid? Let's have a look at an example for illustration. If objects, such as blades of a ship propeller, are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest, at the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. Damage from collapsing vapor bubbles will be shown later. The same amount of water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of a flowing water can be 20 degrees Celsius, which is a vertical line in the diagram. It crosses the vapor pressure line at an absolute pressure of 2,300 Pascal. As long as the pressure is higher, water remains liquid. If the absolute pressure decreases below 2,300 Pascal, water evaporates. The colors in the left visualization correspond to the colors indicated on the vertical axis of a phase diagram on the right. Upstream of a restriction, the static pressure is well above the vapor pressure. The static pressure in the flow decreases as a flow reaches the narrow pipe section. In our example, the pressure at the exposed edge is below the vapor pressure. Consequently, water evaporates and cavitation bubbles are formed. The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 mm in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized short-term overstraining. The material starts to evolve microcracks, and later material can break off. We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Hảo NG. A brand new impeller to the left in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with grey color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function. In this video, we have shown the basic mechanism leading to the formation of cavitation bubbles, which reduce the flow of water. We have also seen the spectacular collapse of cavitation bubbles, leading to noise and damage even to high-strength material. Systems have to be designed such that cavitation is avoided.